is Dr. Chuan Hossan, who is a principal research engineer at Huawei. And before joining Huawei, he was a postdoc and a PhD student at University of Edinburgh, where he completed the work that he is going to present.
Okay, good afternoon, everyone. I'm Chuan Hao, and today I want to share our recent work on satellite image compression called DeepSpace. And this is a project between the University of Edinburgh and the UIUC. So the number of LEO satellites launched each year increase exponentially in recent years, and most of them are used for Earth observation. But Earth observation is where you're sensing from the space. Basically, you put a camera on the satellites and take a picture of the Earth and send them back to the ground station. Today, 1/3 of LEO satellites are used for the Earth observation. Earth observation is supports many critical applications in our daily life. It will go through the world with different trajectory, take the picture, multiple images of the same place a few times a day. And in this example, different color means different satellites with different trajectories, and we use them to cover a large region like California. Then those observation data is used for support some critical usage, like the wildfire monitoring in Greece, some agriculture climate change monitoring, like the Morocco second largest dam, the change over 6 years. And the maritime tracking, you can easily count the number of ships on the surface. So a typical Earth observation system has the following workflow, where you have a few LEO satellites. They keep taking pictures of the Earth, and when there is connection to the ground station, they will send back those images, and then we storage those images on cloud and support some downstream applications. There are 3 key challenges in today's observation system. The first thing is the networking bottlenecks and delays. So the connection between the satellites and the ground station is not very stable. It will just a few times connection every day, and each time just less than 10 minutes. And the bandwidth is also very limited, less than 200 megabits per second. And each satellite can generate more than 1 terabyte data each day. That means if we want to transfer all the data to the ground station, there will be hours to days delays. So it's almost impossible to support latency-sensitive applications. The second challenge is high cloud storage costs. Because there are thousands of LEO satellites, so they will generate more than 2 petabytes data every month. If we put all those data and support hot access on the cloud, then it will cost millions of dollars every month, so it's very expensive. And the third challenge is the computing resources on board is very limited, so it's almost impossible to carry out complex processing on board, because there are only some low-end GPUs available, or even without any GPUs. And to support those latency-constrained applications, there are 3 major requirements. The first one is we are looking for a compression method with significant compression ratio. By significant, I mean more than 50 times. And the second requirement is the algorithm should be very lightweight to be operated on board. And the third requirement is the reliability of those compression methods should be high, because you definitely want to high fidelity images to support arbitrary applications. With those requirements in mind, we look into the existing solutions in the literature. Firstly, if we look at the conventional method like interpolation and compressive sensing, those methods are well developed in theory, and their computing efficiency and fidelity guarantee are quite good. But they are not very powerful on compression. So their typical compression ratio is lower than 10, so it cannot meet the requirement on bandwidth. And if we look at some more recent work, like autoencoders, because those deep learning-based methods are basically black box, there is no fidelity guarantee. You don't know where it makes mistakes. And with some limitation on computing resources, their compression ratio is not very ideal, lower than 30 times. So it's almost on the borderline. And we also noticed that there are some emerging orbital edge computing system that may have some elements that has similar effects for compression. But because they are not tailored for image compression, so their compression ratio is not very good. And therefore, we propose our method, DeepSpace, with image sampling for compression and super resolution for decompression. And it achieves more than 250 times compression on typical data site. This is the first time we bring those super resolution-based method for this task. So we introduced DeepSpace. So basically, DeepSpace will carry out compression on board and running some on-demand decompression on the cloud. For every coming images, we will compress the image according to the inherent redundancy and its similarity to the copies or reference images of the same region. Then on the ground, we will use multiple super resolution models to recover the image. Each of the models are specialized for different regions. You can understand this like a collaboration of different experts or agents. And there are also post hoc measures to estimate the quality of recovered images. If we found that the estimate fidelity is not ideal, then we will send out a retransmission request. Of course, we will refresh the reference hash code to detect the near replicated images frequently. Here is an example of deep space operation. For each input raw images on board, we will cut them into a few tails with the same size. We first decide the initial compression ratio according to the inherent redundancy, and then decide whether to double the compression ratio according to the similarity to the reference. And then on the cloud, we use deep super resolution method to reconstruct those tails with different models. And in this case, we compress those images by more than 130 times, and the SIM is about 0.97. So visually, it's almost identical. So why we think the satellite images can be compressed significantly? So there are two key insights behind deep space design. First is the compressive sensing over spectral domain. This is very some visualization of the compression part. So in this case, we apply a low-pass filter on the image. So basically, we remove. If we look at the spectral, spectrum, we remove all the high-frequency details of the image. And then we just use naive interpolation to reconstruct the image to get the same resolution. So the left side and the right side are almost identical. So that means, in this case, the high-frequency part carries just marginal information. And in DeepSpace, we use wavelet diffusion to reconstruct a specific band of the image, because we just send a few band to the Earth, and the model want to reconstruct the other band according to the received bundle. And the second insight is spend little or no bandwidth on near replicated images. Here is an example about the time series. The time series is the similarity of each region to its first days in our dataset. So in this case, at the beginning, the first 3 months, all the regions in the dataset are almost similar, very close to the first date. So that means there is no need to update those images because there is almost no change. And however, we cannot keep a copy of high-resolution images of the Earth on the satellites. So our solution is we use a binary locality-sensitive hashing to encode the high-resolution image and then send the copy to the satellite, so that we can detect near replicated image with marginal storage overhead and computing overhead. But over time, we observe some seasonal change on the ground. So the features of the coverage will change a lot every few months. This means the reference code should be updated either weeks or months, so that on the satellite we always have up-to-date knowledge about the ground. We evaluate our method on many datasets. It covers most of the region on the Earth, like from California, Hong Kong, and the DN, the Dynamic Earth Network, also covers many selected regions around the world. And we also include both RGB images and multispectral images. So first, compared with the orbital edge computing method, DeepSpace has significantly higher compression ratio, almost 2 orders of magnitudes higher. So if there is sufficient training data, we can achieve more than 250 times compression, while the other OEC method only have compression ratio lower than 10. While achieving high compression ratio, our fidelity on recovery is also the best. So compared with the alternatives on deep learning and other conventional methods, at a low compression ratio, all methods shows high fidelity on recovery. But if we increase the compression ratio, then DeepSpace starts to show significant fidelity gain. And that indicates DeepSpace is capable for high compression ratio compress. So a critical constraint of satellites is the computing resources. So we implement DeepSpace on Jetson graph card and CPUs. Our experiments show that DeepSpace, even just with CPUs, is faster than all other baselines on compression. And if there is lower-end GPUs, like a Jetson graph card operated running on the low-power mode, our method is almost 2 orders of magnitudes faster than all baselines because basically it's only computed as same and running samplings, so it's very fast. To further evaluate our method, we apply the images reconstructed by DeepSpace to some critical applications. We found that the iterated MOE-based algorithm can recover the image with pixel-level high accuracy. There are some applications requires pixel-level fidelity, like the plastic detection. In this example, we use segment anything to detect the object of the image. On the left side is the ground truth, the real image, and the right side is the reconstruct image with DeepSpace. And we count the number of pixels of the objects detected by the segmentation models. There's only 0.015% difference. And overall, on the plastic detection task, with 100 time compression, there's only 2% accuracy loss on plastic detection. To summarize our work, so today, LEO Earth imaging satellites play critical roles in our daily life, from disaster monitoring, agriculture, climate monitoring, etc. And we face some challenges on communication bottlenecks, high storage costs, and the limited resources on board. And we design and propose DeepSpace. We introduce a super resolution-based approach tailored for this system. And DeepSpace achieved more than 200 times compression ratio and is very lightweight to be operated on board. For more details, please check out our code and, of course, read our paper. Thank you.
Thanks for the talk. We have time for a couple of quick questions. Yes.
Thank you for your great talk. And I'm curious, your system, DeepSpace, assumes satellites only downlink directly to ground stations with very limited context windows. Could you explain why alternative architectures such as inter-satellite relays were not considered, and how this assumption affects the generality of your results?
So let me try to rephrase your question. You mean I should consider the interconnection between the satellites?
Yeah.
So at the moment, especially the system we consider when we develop this work, the interconnection between the satellites is not that available at that time. And the second thing is, with this method, even a single second with the temporal, the connection is not very consistent. It can send all the image to the ground. But I do agree with you, if the interconnection between satellites is always available, we can further reduce the latency.
Okay. The second question, I want to know. I want to know why did you compare with the SPLOS 2020 year's best paper from CMU? They used multi-satellite collaborative computing to get computing nanoset pipelines or CMPs. So I want to know why was the CMPs not included in your baselines?
Okay, so actually, again, this is about our the available satellites on the space. There are many satellites without without any GPUs. They only have CPUs, right? Sometimes we talk about the future. Say there is connection between satellites. There are more computing resources, but the already available satellites, they do not have GPUs. Now, how to implement? Right.
The CMP has also have GPUs. They use the Jetson TX2. It includes GPUs.
Yes, I agree with you. But there's many satellites without GPUs, and if there is, say, collaboration between multiple satellites, our method can only be even more faster. Faster, right?
Okay, how about we take the rest of it offline, as we need to move to the next talk. Thanks again.
Okay.